Okay, I think in the benefit of time here, we can get started. So this is the first session, preliminary session for this symposium. So thank you so much. And I think looks like one of our colleagues from USA, Dr. Alkananda, is on line here from Nebraska. So let's welcome Alkananda. Just give me 1 second. So the topic of our talk is going to be artificial intelligence, enable agriculture, foundations, challenges, and emerging directions. And Alkananda Mitra is a research assistant professor at Nebraska Water Center at University of Nebraska Lincoln, USA. So Alkananda, you can go ahead and we have maybe 20-25 minutes for your talk. So please start. Thank you so much.
Thank you. I cannot share my screen. There is the share button is disabled.
Guys, can you display the presentation here? So I think the best way to do it here looks like the PDF file you have sent us. So they're going to play it. So they're going to play it, and then you can just say next, so they can move it forward.
Oh, okay.
Okay.
Oh, sure.
So just hold on for a second. Once they display it, then I'll tell you, and then you can start. And whenever you are ready to move to the next one, you just say next. So these guys will move it forward.
Sure.
Thank you.
In that case, I will just switch off my camera because my presentation is in the other screen.
Okay. Go ahead.
Okay. Okay. Sure. Thank you. Thank you so much.
I think now you can display, so you can start. Thanks.
Okay. Good afternoon, everyone. I am truly honored to be here today and grateful for the opportunity to speak at this symposium on such a timely and important topic. Agriculture has always evolved through innovation, but today we are seeing a new phase of transformation driven by artificial intelligence, data, and digital technologies. To understand where this transformation is coming from and where it may lead us, I will discuss the foundations, the challenges, the emerging directions of AI-enabled agriculture. Next slide, please. This presentation follows a clear path. So first, I will discuss the global challenges that make AI increasingly important in agriculture. Then I will move into the data foundations and core technologies that enable intelligent agricultural system. And next I will explore emerging paradigms to show how AI itself is evolving, followed by key applications that demonstrates its real world impact. And finally, I conclude with ethics, bias, and technical limitation and trust. Next slide, please. This is where the story really begins. The great importance of AI in agriculture is not happening in isolation. It is being driven by a convergence of global pressures that are becoming more intense, more complex, and more interconnected. In many ways, agriculture is facing a perfect storm. Climate variability, water scarcity, soil degradation, labor shortage, and supply chain pressures. and also, of course, the growing demand to feed a rising global population. These are not any isolated challenges. They reinforce one another, and together they are reshaping the future of farming. Agriculture is being asked to produce more with fewer resources under increasingly subtle and uncertain conditions. Next slide, please. This is what the solution looks like to a person. A field is just a plants, but to an AI-enabled system, it is living map of data, a dynamic landscape of signals and measurements. The digital overlay reveals what the eye cannot easily see. Real-time soil moisture, temperature, humidity, crop stress. With drones and sensors, we move from blanket decisions to precision agriculture. We no longer treat the entire field the same way. We target interventions where they are truly needed. The result is better resource use, lower cost, and more sustainable farming. Next slide, please. So where does this overlay get this data or information? It comes from a set of core data pillars that make agricultural intelligence possible. The first, weather and climate records. Second, the remote sensing, which gives us a bird's-eye view of the crop and food conditions. Third, soil sensor, which gives the soil properties, what is happening at the ground level. Fourth, the farm management records provide the operational history behind the field. And finally, the fifth one is ground truth observations, which connect everything back to reality. Validate that the digital picture matches what farmers and researchers actually see on the ground. Next slide, please. Of course, this is where the challenge begins. And this is the data challenge. AI models may look impressive in clean experimental settings, but the real world of agriculture is messy. Data comes from many sources across many skills, with gaps, inconsistencies, and noise. Conditions also vary widely from one region, season, and production system to another. So before we can build any trustworthy intelligence, we have to build trustworthy data foundations. Without that, even the smartest AI system cannot generalize well across diverse farming environments. Next slide, please. To make all of this work, we need more than algorithms. We need data infrastructure. This is the behind-the-scenes system that makes agriculture possible. Agriculture AI possible, right? We need pre-processing to use poor quality data, spatial alignment so that maps, sensors, and machine data line up correctly, and scalable pipelines to process large volumes of information efficiently. We also need metadata, agronomic context, along with governance to ensure security, quality, and proper management. Without these foundations, the digital overlay we saw earlier would not be possible. Next slide, please. Now that we know the infrastructure we have, how does the data actually move? And that is the data flow. The data starts as raw, fragmented inputs, like weather reports or soil readings, and travels to the infrastructure pipeline. It is here that the raw data is refined, standardized, and ultimately resulting in the reliable and scalable AI models that actually power the farm. The flow is the journey from raw noise to actionable insight. Next slide, please. This slide shows the AI ecosystem in agriculture. as a layered system. At the bottom, we begin with the data collection using IT sensors and remote sensing. The data is supported by the data infrastructure like cloud and edge computing and data pipelines. In the third layer, it comes the AI models such as machine learning, deep learning, spatio-temporal models, and so on, and which turn the data into insights. Above that, it is the trustworthy AI, which ensures the system is explainable and secure. And finally, all of these supports real agricultural applications like robotics, automation, or decision support system. So the key message in this slide is that successful AI in agriculture depends on the full stack from sensing to trusted. There are a couple of emerging technologies. They are digital twin and quantum machine learning. So the first one is digital twin. A digital twin is basically a virtual representation of a real agricultural system that is continuously updated with real-time data or real-world data. It allows us to move beyond observations and into simulation. Instead of testing every decision directly in the field, we can first explore what if scenarios in the digital environment. For example, we can simulate drought, irrigation changes, or crop stress responses before implementation in practice. This supports risk-free experimentation, faster learning, and more informed agricultural decision making. So a physical system, and that is the relation between the physical system and the digital twin. Another emerging, next slide please. So did we reach the slide for the quantum machine learning?
It says I think it's number 10, I think. Whatever is 10 is emerging paradigm.
Okay, okay, so digital, this is the digital twin. So this is the one of the AI emerging paradigm. A digital twin is virtual representation, as I said, and it is the replica, or I will say, of the real world data. So here it is more we do the experiment. So next slide, please. Another emerging frontier is quantum machine learning. While it is still in the early stage, it offers interesting possibilities for agriculture problems that involve very high dimensional data, complex optimization, and large interconnected systems. In the future, it may help address challenges related to climate modeling or genomic analysis and decision support across broader food systems. So while this is not yet a routine tool for the farm, it is an important area to watch as agriculture AI continues to evolve. Next slide, please. So far, we have discussed the foundations. Now let us look at where AI is already creating value in practice. This slide shows that AI is already making an impact across multiple dimensions of agriculture. It supports crop and soil management, improves irrigation decisions, enables earlier detections of pest and disease, strengthens yield forecasting, and so on. Across all these applications, the common goal is the same: better decisions, more efficient resource use, and more sustainable farming systems. Taken together, these applications show that AI is not replacing agriculture. It is augmenting agriculture with decision making. Next slide, please. As AI becomes more involved in real agricultural decisions, performance alone is not enough. So the trust becomes essential. We have seen the data, the models, but now we come to a central question. Why should a farmer trust the AI? If an AI system recommends a costly or high-stake management action, the user needs to know or understand why that recommendation was made. This is where explainable AI comes. This helps make the model decisions more transparent through the three important dimensions. First, model understanding helps reveal what factors influence the predictions using tools such as feature importance. Secondly, the uncertainty estimation helps communicate how confident the model is in its output. And thirdly, visualization tools such as saliency maps or heat maps, they help show where the evidence is located in an image or in a field map. Together, these approaches make AI outputs more interpretable and actionable. By combining AI precision with human expertise, we create decisions that are not only faster but also more trustworthy and grounded in reality. Next slide, please. If explainability helps us trust what the model is doing, security helps us trust the system it is running on. As we move agriculture further into the digital age, cybersecurity becomes a core concern. Trustworthy agricultural AI depends not only on good models, but also on secure data, protected pipelines, and resilient systems. That means securing information as it moves across devices and platforms, defending against tampering or adversarial attacks, and ensuring strong access control. Technologies such as encryption, anomaly detection, or provenance tracking, federated learning can help build that protection. In this context, security is not only a technical issue, it is part of agricultural resilience and food security. It is a connected agricultural future. In a connected agricultural future, protecting data and AI system will be just as important as moving their performance. Next slide, please. So after looking at the opportunities, it is equally important to ask what might limit impact in the real world. Now we need to look at the balance of this technology. The benefits are clear. AI can support higher productivity, reduce chemical and water waste, improve resource management. But the challenges are equally real. Data standardization across regions, production systems remain difficult. And the cost of digital infrastructure can limit adoption, definitely. As we move forward, we must ensure that these benefits are not confined to the most well-resourced farms. Otherwise, we risk deepening a digital divide rather than building a more resilient and sustainable agricultural future. Next slide, please. So, after looking at current applications and present-day challenges, the next question is, where is this field going? Several trends stand out. AI is moving closer to the field with their distributed intelligence, definitely. Learning is becoming more privacy aware through federated learning. Models are becoming more powerful by integrating multiple data types into unified systems in combination models. Hybrid modeling is making the black box AI technology to more supported by the laws of physics and biology. Swarm robotics are coming, so that instead of a bigger machine, we are seeing a lot of smaller machines, and so more precise agricultural intervention. And finally, that is decentralized trust, like technologies like blockchain. Next slide, please. As we conclude, we must remember that AI is not just a technical tool. It is increasingly part of the decision-making process in agriculture, because these decisions affect food production, natural resources, and livelihood. Ethical deployment is essential. For AI to be truly successful in agriculture, it must be guided by fairness and inclusion, so that its benefits reach the farmers and the stakeholders broadly. By sustainability, so that its recommendations support long-term environmental health. And by responsibility, so that it protects farmers' interests, privacy, and surrounding ecosystem. Ultimately, the goal is to create an AI system that are not only intelligent, but also ethical, trustworthy, and aligned with the needs of agriculture. Next slide, please. We started today by looking at the perfect storm, the massive challenges that threaten our global food security. But we have seen agriculture is not powerless in the face of these challenges. Today we have tools that allows us to see more, understand more, and respond more intelligently than we did before. AI is opening new possibilities for how we manage agricultural systems. But the future of AI-enabled agriculture does not rest on algorithm alone. It depends on three essential foundations: data, trust, and of course, responsibility. By 2050, we will need to feed nearly 10 billion people under conditions of increasing uncertainty. AI is not a complete answer by itself, but it can be a powerful bridge between today's agricultural challenges and tomorrow's more resilient solutions. It helps us move from reaction to prediction, from uniform management to precision decision making, and of course, from uncertainty to a better understanding. If you get this right, the future farm will be more productive, more resilient, and more sustainable than ever before. Thank you. And next slide, please. If you want to collaborate with me, I already mentioned my email address in the last slide. And you can connect with me in the LinkedIn and can have a look at my work on my website. So that was all from me today.
Thank you. Thank you, Dr. Lisa. Thank you for this wonderful presentations. Yeah. So I think we can take, if there is any question from the audience, so maybe one or two. If anybody has any question for Mitra. Yes.
Dr. Sananda, can you hear me? Dr.
Yes.
Anand, this is R.K.
Yes.
Panda. This is R.K. Panda. I have some clarification rather. You are associated with the development of crop growth models with USDA. Okay, the crop growth model, they are developed for certain set of conditions. And then, we use that globally. Let's say in India, the conditions are different, exact genotype. If it is there also, the soil, the other environmental setup is different. We calibrate, validate with our data, and use it. Okay. So what I'm saying, it is also a complicated data-driven model. In a way, how can the AI be used with less data than the crop model uses? And can it be little more location specific than the crop growth model, which are very intensive models, or it can support, it can be integrated with crop growth model and it be used for local conditions rather than the place where it is developed. Did you get my question?
Yes, thank you. Yes, thank you for the questions. It's actually wonderful questions. And as there are two parts of my work. As a training, by training, I am a computer scientist, so I work in AI and agriculture and computer vision and some context applications of AI. Similarly, I work in the USD areas, like collaborate with them. So I am stationed in USD. So here in our lab, in the adaptive cropping system laboratory, those models we are using, that is the crop models, those are process-based models as you mentioned. And right now, those are process-based models, and they are accessible through a desktop application. Its name is Classing, and we are also making the web development. But the thing is, if someone, a farmer, needs to use an application like in mobile, these process-based models, we cannot use it because they are heavy. So if we need a server, we need a big machine. So of course, AI can help. And actually, in the near future, not only the right now maybe there are an AI crop model which is not so strong as a process-based model, and there is a strong process-based model which are strong, they give a lot of information, but they take a lot of resources to run. So in those cases, what happens? There is no bridge. So in future, near future basically, there will be hybrid modeling where the information or the output from the crop model, the process-based models can be used through AI and more portable through mobile application or anywhere where the user, like the farmer or stakeholders, can use. And I feel like that will be the best way to use the process-based and the AI models together.
Thank you so much, Dr. Mitra. Just to have a quick clarification, myself, you mentioned about data protection. So, so typically in US, there's a fair data policy. We usually want to share the data we collect, and that is one of the challenges. So, what is your take on that? Because you mentioned that you have to protect the data, contrary to what the US norm is.
Definitely.
Thank you.
So basically, when we talk about data protection, there are two types of ways we can do. The basic way is like anonymous data, right? So when you are making any kind of application, see, for any AI model, when we are making it, our goal is to make something so that people can use it, right? Like an application, any type of. So in those applications, if farmer and user who will be using or providing the data, they need to make sure, like, okay, my data and the application is not sharing to others. So there are ways we can save the data to the user account with proper encryption. Different types of encryptions are there. So definitely, and there are other ways like edge computing and fog computing. Those type of computing paradigms are coming where the data actually does not, or federated learning, where the data does not move actually from the location of origin. So in that case, if the data stays with the origin, stays at the origin with the farmer, there is no need for different types of inflation. So we can address it in different ways.
Okay, thank you so much.
Yeah.
So thanks for your time, and I'm sure it is pretty late in Nebraska, so thanks for taking
I'm
time.
actually in Eastern time. I'm in Washington DC.
Okay.
So it is 3:21.
Okay.
Yes.
All right. Thank you so much for your efforts.
Thank you. Okay, bye.
Bye-bye. All right. Good afternoon again. I just want to rephrase what Dr. Mishra said, but in addition, I will try to dovetail to what her last comment was, to bring physics and the models and the processes into the fold to join with AI. As I said in this morning, we are still starting to work, so it is not quite there, but at least I will give you the concept that what we are going towards and how we can make it more efficient. Anyway, so a lot of these are visionary. These are all these information, so as I said, are hypothesis, not proven, but we are working towards it. So these are opportunities, and I'll also share some of the challenges that we encounter not only in India but also in US. There are many challenges when we deal with AI and the data sharing and all those stuff. So this presentation is towards that. Okay, just to 101, because a lot of students are here, just to give you a briefing of 101 on AI, and everybody knows about it, but just to have a completeness. So, you know what is AI code? It's somewhat like a machine learning or a deep learning toolbox, and you can put all those information that you collect the data into action, learn from something, and get out from the data and try to make a decision. So that is what essentially is all about AI in a nutshell. So the deep learning and the artificial learning, artificial network, there are many, many tools that have been evolved in this last several years. You can adapt, improve, and go forward in various decision making in agriculture. So these informations are primarily looking into just like mimicking a human brain, although it's not perfect human brain, but that is what we are trying to do through artificial intelligence, to mimic the human brain, how we think, how we connect the information, how we connect the dots, and come up with a conclusion. So that is what essentially we're trying to do. So these elements are interconnected, and they're working in parallel or in tandem sometimes, and learn by example. This is like a recognition of patterns through examples. That is what AI is all about. But it cannot be programmed for a particular problem or a particular case. It is more generalized. Output or optimum information. So that is kind of our obligation as human being to use the AI. That is what I was trying to mention this morning, that we have to use it responsibly. That means, suppose I say, okay, how many chairs are here and how much water is flowing in the river? You can connect, you correlate, but does it make any sense? So those essentially are our responsibility to think, to write information, right context, right connections to make those inferences. And find out how to solve the problem themselves, by themselves, in other words, that how you connect the right information, maybe from physics, biology, chemistry, to connect them to get to attend to these questions at hand. just to give a very simplistic picture, what you see, like suppose you are looking at a picture, your brain is thinking, okay, this is some gills, this is some pins, and this is like a streamlined body, it must be a fish. Or it is something more like a long face, it is a white and black stripe and 4 legs, it must be a zebra. So how can we connect these patterns or attention to certain particular details can give you the inference or that information that you can connect with. So that is essentially is all about AI. There's nothing more or less, but in various smart ways you can do, design, propagate those information. So in our context, here in agriculture, in artificial intelligence, just to give a simple Bayesian artificial network, where you can give the information that is related to, let's say we are talking about the input of genomics, what kind of plants, what kind of genomic traits of that plant, we can give as input. We can also give like some kind of natural resources, what kind of soil is there, what kind of land or other water resources, water quality aspect is there, you can also give as input in the context of our problem. Or you can also give crop management practices, tillage practices, cover crops, rotations. All these features can also go in as input to the system. And maybe climate, of course, there are uncertainty, there are precipitation, temperature, humidity, etc. that can also go into this input. We know all these things influence your agriculture, but we don't know how they interact, how they correlate, how they together as holistically attend or influence your practices or your agricultural yield, those kind of things. Why I'm saying this, that because a lot of times these things are very complex. The systems of agriculture is quite complex, so that is why all these inputs are necessary to go into your decision making. So in between there are a lot of in between there are a lot of these intermediate steps that is processed in different ways, and there are kind of different kind of summations, and there are functions, transfer functions that relate the input and go to the output. In this case, let's say yield, or we are talking about profit, or we are talking about water, whatever it is, that it relates without knowing what is going on in between the steps. So there are various different techniques and learning processes like associative mapping, like auto association or retro associations. There are different regularities detection. There are different fixed network, adaptive network based on the problem, and supervised learning or unsupervised learning. If somebody is sitting there observing the outputs and trying to say, okay, it makes sense, maybe this will be the next step. And or it is unsupervised, the machine itself is learning through this process and giving the direction to the next steps. So those are the things that is what people have been working on. There are new artificial networks that also picks up some of these very specific nuanced features, and those nuanced features can detect which way to go or which way to block. So those information and those techniques are evolving and can be utilized for various different applications such as agriculture or in any other fields. Most of the problems that we deal in these kind of systems are nonlinear, uncertain, and many of these occasions are non-stationary. That means whatever we predict now may not be valid tomorrow, because as we know, the climate is non-stationary, a lot of things are evolving. So whether what we produce today with the network, is that going to be working for the tomorrow's system? Spatiotemporal data fusion, some of those things are important, how to bring those information, multi-resolution gap filling. Most occasions, our complaint is we don't have enough data. Even if we have data, there is not enough to what we are trying. How can you fill in those gaps, and you can explain the data sets are really making a difference because those data sets are gap filled in a proper way that gives you the right information for the right reason in data mining, etc. Some of the challenges that we encounter in agriculture, and that is very important to realize. A lot of times we just think, okay, I can take this information, I produce AI, transfer, apply. Not necessarily true. I mean, particularly in the context of India, because we deal with, as we already know, that we are talking about our land holdings are small, our crop varieties are plenty, our culture is different, our food going from south to north is different, many of these practices are all different. So how can you take this one information, one network, and apply to various different systems, various different crops, various different practices? And that is also applicable to US context, because most occasions agriculture is very much local. The farmers' practices historically from their grandparents, and they continue that. If you try to force them, they won't change. So that is the big challenge. Inability to tightly control the conditions. Many occasions, some of the things that happens are we cannot control. The weather, the practices, the pest, and all those things, and we get those data sets. So how can you use those information under those network under those kind of systems? Many occasions, like in the American context, of course, here is also true. Getting there, like we have huge combines. They're like $1 million. And suppose somebody investing $1 million combine to harvest these crops, we can rotate it out in 2 years. So we have to have a new system now, and we have to adapt it. Because they have to run it for next 25 years. That way they can make their profit. So those are some of the challenges. And it is a painfully slow process. If you miss today's drought, tomorrow's flood, something else is happening next, we cannot repeat it next door until something else happens next year. So this is a very slow moving process because we depend on nature and a lot of those things happen that way. So in other words, we have to be patient, we have to collect the information. So agriculture is not that easy to deal with through AI, even if we talk about it. Past performance doesn't give you the confidence that you can also predict future, because you are dependent on many of the other factors that is evolving. So those evolving scenarios need to be attended in this context. And a lot of the stakeholders, they are deeply interconnected. Maybe we just think about a farmer. That is not true. I will just show you in the next slide how connected and interconnected the systems are. And if this one system fails in one point, how the trickling effect goes around in the entire system or the system of systems here. And agriculture is AI expertise deficit. Of course, we are trying to pick up some of those things, but it is truly, we are not doing yet the necessary things because it needs a lot of other technological know-how that people are using in health sciences, computer, driving, motors, and all those kind of things. But in agriculture, we don't have enough expertise to attend to these questions. So just to give you a perspective, what AI can do in their decision-making processes. Just like we talk about this IoT, data coming from different sources, natural resources management and conservation, or you can do various data analysis that comes from like genetically modified crops or economical policies or incentives given to farmers. Together need to be attended to give you the answer, and these things can be assisted by this AI for the decision making. But more importantly, that how can you take this information from a local scale to regional scale to this national scale is very, very important. And how can you do that? That is where it is a multi-pronged approach where you need to bring in into education, research, and outreach to the farmers in the same platform. That essentially means you have to do research, get feedback, you need to educate the people who are the stakeholders, and also outreach, basically reaching out to those people and training the next generation of students to do better things or improve things. That is what you need to do. So this is just an example of how interconnected the systems are in agricultural thing. So if we just look at the farmers and their certain particular point, like number 8, farmer level decision making, that is not the entire picture. Because maybe that will also pollute the water, or irrigation is going to be water is going to be shortage somewhere, or supply chain is going to be broken somewhere else, or climate is going to be not supportive of that. So this whole thing is interconnected. So how can you attain your decision making while attending to this entire picture, which is non-stationary, non-linear, and moving forward together? So that means essentially if you just take a farmer level decision, not necessarily that is always going to give you the right answer in that particular thing. You need to attend to this other thing, that way they can make the maximum profit or maximum yield or conserving the water resources and protecting the water quality and all those things together. Some examples of these decision-making systems for natural resources. For example, that is where I come from, because I work in water and soil. So you can say the optimum status of soil moisture, where you can, or temperature, where you can plant the seeds. That way you can get the best, the maximum growth of the plant or the germinations. Determine the suitable crop traits. What are the particular combination of soil and all those features that can give you the best possible system with cropping practices that that can give you the best productivity as well as protecting the soil health or soil carbon sequestration, those kind of things. And locate hotspots, because those are some of the hot moments where you can do some adaptive fertilization, defining dose and timing or maximizing the profit and or yield, minimizing the inputs. Those things are necessary decision making processes that a farmer or a decision maker has to do in this chain here. Analyze long-term climate data, rainfall, temperature, evapotranspiration, and optimum irrigation requirement, etc. Are the how it has to be done and how to analyze them and their operating costs. And discover different management practices, including tillage, cover crops, crop rotation, residue management, and all these on-farm and off-farm water quality protections. So, in other words, you have to find the optimum land and crop acreages in their overarching regional and spatial-temporal distribution, that you can attend everything together, that you can protect the soil resources, water resources, enhance the profit margin of the farmers, reduce the water quality issues, and all those things. So these decision making are kind of the questions that you have to pose to attend to this agricultural system. With that, I just want to move on to another maybe 5-10 minutes on the next topic, because we talk about the physics, the chemistry that goes into this artificial intelligence that can supplement artificial intelligence and make it better. So that is where a lot of opportunities are there, a lot of challenges are there, and we are trying to resolve through various different research. So this is kind of the perspective I want to throw here, is that the classical perspective, because many of the data sets that come are different scale in space and time. How can you assimilate those information from different space and time into your artificial intelligence or in a process models that can help enhance the efficacy or skill of these artificial intelligence tools that you are going to use for? So this is essentially a multi-scale, multi-platform soil moisture data. That is where a lot of work has been done, and soil moisture is kind of a gatekeeper to hydrology, for agriculture, and many other things that you deal with. So in those cases, we try to look into these processes like various topographic features, vegetation types, soil types, and your land surface characteristics that can contribute. But at the same time, you need to look at what are the sensors that are going to give you the data, remote sensing, ground sensing, and their uncertainties that come along with that. In other words, you need to just don't take a 36-kilometer footprint of a satellite that is revolving around the globe, or you just take one snapshot, one point in a particular field. You have to fuse them. You have to use all of them and take the processes accounted that you can make your AI more efficient, and because you bring the processes into this world. We have done a bunch of work, and I would recommend that if you are interested in specific things, you can always explore to our website and you can find more details. I'm just going to touch on some of these basic concepts that what we have done. So in this particular work, if you look at the left-hand side, we have a data model, that all the data coming from the local point scale data all the way to the satellite data. We also have the process models, like topographic features, how the water moves through the terrains, how it moves to infiltrate through the soil systems, how it uptake by the plants. All these are processes that are also contributing to this whole water balance, energy balance. Or you know a lot of statistics, a lot of parameters, legacy data, a lot of these soil maps, other maps, those information can also be utilized. And those information together can give you the perspective, how can you bring in these processes and the other things to address a multi-scale soil moisture feature that can be utilized at the field scale for farmers, or it can be used at a large scale for weather and climate predictions or flood forecasting, those kinds of stuff. So in other words, you can generate this information and feed in those information for your decision making in your artificial intelligence toolboxes. So this is another thing that we talk about class drought, and that is a pretty significant issue for various agricultural practices. And how you can judge it? Because unless otherwise you have a bunch of sensors on the field, you cannot do it. But we have a lot of tools. NICER, which is upcoming and actually is now, flying over us for past 6 to 8 months, is going to contribute a lot of high resolution soil moisture data. If you take those data sets and plot them at each individual pixels and see the dry down patterns, you can find out how the dry down pattern sits and where they sit. That can reflect various processes, that is gravity drainage, energy limited drainage, or there's other processes like diffusion dispersion, or your limited water conditions, that is where your dryness changes, and the coupling between land and atmosphere also shifts. So those information can give you a broad picture across the globe, including India or America or Australia, it doesn't matter. You can find anywhere and everywhere these patterns that can give you that information which you are looking for. And these patterns are going to be very useful for decision making. This is another one. We are trying to show if not necessarily only the patterns, you can also get some thresholds. That means where it breaks, where it changes path. And those paths are going to be important to describe whether the field capacity, whether this soil moisture trend out, or whether the information is going to be at a weakening point, that means plant is going to die, and whether we can intervene, the farmers can irrigate or do those kind of things. These information can help through this remote sensing data at any location globally. And we have developed those kind of techniques and put in our website globally on a daily basis. So anybody can go to our website and find out those particular locations, and they can say, okay, this is at the weakening point, or this is at field capacity, whether and how I should manage my soil, how I manage my agriculture to protect from the pest or protect from drought or protect from anything else that we are trying to do. This is a flash drought platform we created, and that is globally. People from Europe to Latin America to various places are using this platform just based on the soil moisture data collected through remote sensing. And now with the remote sensing platform NICER, now flying, which is a combination of NASA and ISRO collaboration, will give you 200-meter resolution data. We really don't need any data points on the ground. I mean, if we can evaluate at different locations, you can use this information and locate where the drought is going to happen in the next 2 weeks. That way, we can prepare our farmers, our stakeholders, and give the decisions. That is going to be very helpful to make this management possible. And these things are powerful and generalizable, and it is global. This is another work that we have done here to reflect, also to see the tipping points. Tipping point essentially means where the shifts are happening. Suppose some conditions are like, if you are looking in the desert conditions versus wet, humid conditions, you can see whether they are mostly in dry scenarios or wet scenarios, or some occasions like in India, they are like shifting left and right, essentially saying dry to wet or wet to dry. And these informations are very useful to manage our agricultural practices, because we know that these certain things are going to happen certain ways. And these informations are also, we have created some particular tipping characteristics for the soil moisture by taking their mean tipping depth, how deep or how dry it can go, or how long it is going to stay, or how many times it is going to happen across a year. So if we know these features, and we can create such a triangular diagram, you can see what kind of soil texture creates these kind of systems, which is more dry or wet, which kind of climate systems you will be more prone to these kind of droughts and floods, which kind of plant functional types can give these kind of systems. So by assimilating this information together, you can be more proactive, and you can design your agricultural systems and your other systems to attend to those ecosystems, to attend to those kind of natural resources, challenges under climate variability. That is what we're talking here, right? Climate smart agriculture, climate smart ecosystems. And these informations will be collected and created are going to be tremendously tremendously useful as the first step towards it. More lately, we have come up with the physics and processes. We talk about how the plants uptake the water. I'll stop in another 5 minutes here, 2 minutes. So essentially, we talk about how the soil moisture and evapotranspiration are coupled. This is the backbone of agriculture, plant system, ecosystems. How much water is available on the ground, how much water is uptaken by the plants, and how much is thrown into the atmosphere. This is a very fundamental challenge or issue. If we can resolve it and we can know it, we can fill in a lot of gaps, because a lot of times data is not enough. So this recent work where you are trying to see the coupling between these different systems and how the water collected today from precipitation, or how much water was collected yesterday or day before yesterday, is contributing to the water that is uptaken by the plants today. Isn't that very important information? Because the water that falling today is not necessarily what is uptaken by the plant. What was there before for past 2 weeks is more important, or what is going to happen next week, today's event is going to be more important. So this information we are trying to find out by optimizing some of this and the nature how they move. So the ET at a particular day, how they're connected to the preceding days of the soil moisture is kind of focus here. So we come up with a very novel least action theory, and everybody is now attending to this paper we published recently, and that gives us the information that how the moisture is taken up by plant, which was collected over the last several weeks, and how it's optimized by the plants, taken up by the system. This information can really enhance our capability for the optimization of agricultural practices. I just want to show that here, that we can also go through the details in this particular paper that was published last year in Water Resources Research. And primarily, if you look at the left-hand side of the figure, we are talking about how these different soil moisture coming from different days accumulated and taken up by plant on that one day, and these recursive things are happening on a continuous basis. And this information is very valuable for managing your water for agriculture. And we also verified that information by different routing systems in arid climate, humid climate, and isotopic studies in different globally, in using a lot of data sets globally. So with that, I would just say, if I know something from satellite, let's say ET, can I convert that to soil moisture? That can give me the efficient usage of the information that can be useful for planning my agricultural practices. So this is what we're trying to do here. That means I know, let's say, ET from a remote sensing platform. Can I use that to detect my soil moisture on the left-hand side, which is blank right now? I can, through this process. That way I can know how much soil moisture is there to give me that particular ET scenario. So this is a very important information that can give you, bypass a lot of things and give you the right answer for the right reasons. If you bring this together to your soil moisture and ET and your artificial intelligence, you can make many decisions and protect from drought, flood, cropping practices, pest control, etc. in this environment. With that, there are a lot of things, open problems. Many satellites have been flying for the last 30, 40 years, but more recently, this NASA and ISRO satellite is giving a lot of extremely good data in different bands. I suggest all of our young students and new colleagues to use those data sets for various approaches that we are talking here, climate smart agriculture, or anything that they're trying to do. So this is where I will end here. Thank you so much for listening to me, and hopefully this is useful. Thank you. If there are any questions, I can attend to now.
Sir, please be there. Boy is going, sir. Sir, you can now sit, please.
This is a good welcome for a nice presentation. Really, it was enlightening for us, at least for me, how to go for AI, and particularly soil moisture study and all. Shall we understand that there is a strong interaction between soil moisture and the nutrients? This is one part. Second part, we are trying to correlate the AI in sustainability. Now, over the years, agricultural scientists and all other scientists also, they have undergone several challenges, and they have adopted some technologies, findings adopted by the farmers. Acceptability and adaptability are two different things. One is accepted, but cannot be adopted. So my question is, is AI going to further encourage the chemical farming? Why I am saying this? The government policies do encourage what type of agriculture should take place, how the agriculture will be transformed. Not only central government from the Indian government, but state governments also. They are emphasizing on sustainability through organics. So, chemical we have, this is the moisture content, this is the nutrient applied, how we know the release pattern, all those things. But can AI be equally effective when we go for organic way of growing the crops? Debatable things are there, of course, but where we do not know the well-defined pattern of release of nutrients, we use different organics. So how AI is going to address those things, or AI is simply about chemical agriculture influence?
Excellent question. I mean, and I should admit my ignorance here, right, over the Indian context. But even in US, nutrients is a big aspect, just like moisture, nitrogen. Those things are important for the productivity. So in those cases, we don't have any, let's say, in a local scale, in a field scale, we measure it, monitor it, and translate that information to something useful in a AI context. But what I was talking about in a global context, this is still far-fetched. In other words, we cannot really measure nitrogen, for example, in the soil at this moment using any satellite or any of global platforms. So in that case, we still can, if we have some data, collect on this particular organic farming places and collect this data maybe for a couple of years or a few years, and use and fuse the data with the other platforms of soil moisture from remote sensing, from ground information. We definitely can make a first step towards it. May not be the last step, but maybe to start with that way. But your point is well taken, that we should also try to develop some sensors that can give you more these kind of information in addition to the current state of the knowledge. But those things are yet to come, and we are actually, personally, I'm working towards it in some occasions, some of this nitrogen and carbon things into the, how to monitor from different hyperspectral, local, and in situ sensors that can fit into those kind of organic farming, for example, or in other kind of contexts. Thank you. Hopefully I answered your question. Thanks. Thank you so much.
Thank you, sir. So, with kind permission, may I invite the next speaker in the session, Professor C.R. Rai, Director Nebraska. His talk is on water, food security, and global challenges. And Professor Rai is already here. The warmth is not coming. I believe we should have a small gesture of clapping, so that कहते हैं मुस्कुराइए ऐसे कि बाहरों को होश आ जाए, मुस्कुराइए ऐसे कि बाहरों को होश आ जाए, जब से ताली बजाइए ऐसे कि बोलने वालों को भी जोश आ जाए यार. Have a big round of applause. These people are prepared so hard, you know. There's a small change. Professor, I will be speaking at last now. May I request Dr. Jude Coby to please take on. You have been knowing him. He is a senior program manager at University of Nebraska Lincoln USA. He will be speaking on agriculture, water use, and India, Africa, India, USA collaboration. He has been working so long in this area. I think he will give a brief insight. And Professor thank you, thank you. Okay. Sir, would you like to take over? Please, please.
Thank you. Great, thank you very much. Good afternoon, everybody. And thank you again for giving me this opportunity. So I'm going to talk a little bit about, zoom out a little bit, talk about agriculture and water use in Africa and India and the United States. Here's a quick outline of what I'm going to be saying. I'm going to talk a little bit first about Africa's food security challenge in the next 20 years, and I'm going to try and emphasize to you how short time is, how little time we have for this, to deal with this. I'm going to talk a little bit about irrigation, water resources, and the global water crisis. I'm going to talk a little bit about agriculture in Nebraska, and then building on what my colleague was saying earlier about the complexity of the systems problem that we face in terms of global food security, and I'm going to try and draw that out a little bit, and then I'm going to talk finally about how I think artificial intelligence can help us with that. So, just transport yourselves to Africa for this slide. So I put this map together just to give you a sense of the size of the continent of Africa. It takes up about 30% of the land's surface of the earth, and there are 54 countries in Africa, and the total size of over 30 million square kilometers. And I've put in there just 4 land masses in random: Australia, Western Europe, the United States, and India together. And Africa is bigger than all 4 of those put together. We currently have a population of about 1.5 billion people on the continent of Africa, but we expect that to go up to about 2.5 billion by 2050, which is very soon. It's just around the corner. Africa has the youngest average population of any continent, median age of about 20. Currently, about 2/3 of all Africans are employed in agriculture, normally in small-scale subsistence agriculture. It's a continent that currently relies on average on food imports, and food insecurity, vulnerability, instability, and crisis are all possibilities for the future that we want to try and avoid. And indeed, the governing, the body that governs much policy across Africa, the African Union, is putting a renewed focus on food security. This is a chart that was developed by the World Bank, and just to show you that we have the incidence of extreme food insecurity and poverty across the globe has increased radically since 1990. We have indeed a problem of rising poverty rather than poverty decreasing in many areas. About somewhere between half and 3/4 of all people in Africa depend on groundwater for their domestic water resource use, and I'm going to be talking a little bit about groundwater as we go as well. Here's another chart just to show you that severe food insecurity is a growing problem in Africa, and to what extent that differs from the rest of the world. I'm going to talk a little bit now about irrigation in Africa. So the brown area there on the chart shows you what we call the dry lands in Africa. They're only about 43% of the area of Africa, but they support 50% of the population and include 75% of those who are in poverty. So just take a little snapshot of that dry lands area in your heads. It's important, and I'll talk a little bit more about why that is in the next couple of slides. So currently, in any area subject to very variable rainfall, variable and low rainfall, such as the African drylands, the obvious solution is to irrigate more, because irrigation can insulate you from the kinds of insecurity that erratic and changing rainfall can bring about. However, in Africa south of the Sahara, only about 3% of the arable land is irrigated. That's about 7 million hectares. But those 7 million hectares produce about 1/4 of all of the food in that area. So irrigation is a huge boost to productivity and efficiency of land use. And just to give you a sense of the scale of that, currently India irrigates about 80 million hectares, and the state of Uttar Pradesh alone is about 14 million hectares. Take you back to the sub-Saharan African figure of 7 million hectares, just as a sense of comparison. So the other thing I don't need to remind anybody in this hall is the importance of rural agriculture as underpinning economic development and its incredible impact on poverty alleviation. So my hypothesis from this slide is that in Africa, did we miss the Green Revolution? What happened in Africa? Why don't we grow? Why haven't we seen the same gains in irrigation and food productivity as regions such as South Asia? Just another slide to show you how little irrigation in sub-Saharan Africa is as a proportion of the total arable area, or the total harvested area. We have a very small proportion of that is irrigated. And if you remember back to the slide on the dry lands, that's despite the fact that we have these very arid, very variable rainfall areas where irrigation would be something that could insulate us against the kinds of low crops, drought impacts that we do experience. One more slide here showing you this in sub-Saharan Africa. The chart divides us between water scarce and not water scarce areas, and you can see that in water scarce parts of Africa, in those dry lands, we irrigate even less as a proportion of the arable land than we do in not water scarce areas. So you'd expect it to be the other way around, where the more water scarce an area is, the more we irrigate. And in fact, it's not. The more water scarce an area is, the less we appear to irrigate. Just another couple of charts here showing you, for example, the difference between groundwater availability and use in sub-Saharan Africa versus in India, and the total areas of arable land irrigated in both of the regions, comparison with India. And given the relatively low rates of irrigation in sub-Saharan Africa, you would expect that the rate of increase in irrigation would be higher than anywhere else. We have, after all, a huge amount to catch up. In fact, the data that I have there between 1973 and 2013 shows that, in fact, the rate is only about 1/10. It's an order of magnitude lower than South Asia and only about 1/5 of East Asia. So not only are we irrigating a relatively small proportion of land, not only do we have the huge challenges of dry lands and increasing rainfall instability, but the rate of increase in irrigation appears to be growing more slowly than in other areas. Just very quickly, this is all in the context of a global discourse of water shortage, and it's often quoted that we have this global water shortage. It's been mentioned in numerous journal articles. You can see it in numerous press articles. Here are some titles of papers and relative high-impact journals relatively recently, which puts another constraint on our efforts to improve irrigation in sub-Saharan Africa. We can see, however, if we look at the data, that in fact we use very little of the available renewable groundwater resource across most countries in sub-Saharan Africa. We think we have approximately 1,400 cubic kilometers per annum of renewable groundwater, and we currently use only about 20 of those cubic kilometers per annum. And to me, this just shows that we have the potential to expand, to double or to triple our irrigated area without significantly impacting our water resource. Another way to put that is we're nowhere near the ceiling that water resource availability on average can impose. Just a couple of headings there. As I mentioned before, the African Union has got very firmly behind improving agricultural output in a range of ways, and in particular improving irrigation and water use and water management. So all of these initiatives, by the way, emphasize partnerships, and I'll talk a little bit about partnerships in a slide or two. Collaboration and cooperation is the way forward. Just a quick slide to bring my current home state of Nebraska into this. And Nebraska, for those that don't know, is a leader in the United States in total irrigated area, 3.4 million hectares. And if you remember back to the slide on Africa, that's about half of the entire irrigated area in sub-Saharan Africa is currently irrigated in Nebraska. More than 90% of that irrigation water is from groundwater from the High Plains Aquifer. There are 96,000 registered irrigation tube wells or boreholes. And the two other things to take away from this slide is despite the increases in maize yield in the chart with a black line on top, we've had a steady fall in the amount of water that's used per area of crop. So in other words, we're getting more crop with less water. So just to show you, this won't surprise anybody in this room, you've been doing exactly the same thing in India, but we can get more crop from less water with some of the newer techniques that are coming out, including AI-powered innovation. Again, just a quick reminder here of some of the impressive achievements that have been done in this country from the 1960s onwards. The big surface water combined power and irrigation schemes, the huge expansion of tube well irrigation across India, combined with the rollout of rural power availability and small submersible pumps. New innovations now, drip irrigation, better seed, solar power, have further boosted agricultural outputs. And alongside all of that has been what I sometimes think of as a silent transformation in the economic, the political, and the institutional systems that underpin, that enable that irrigation and that improved crop productivity. So all of this means that India now has one of the largest irrigated areas in the world, supporting food security for the entire population. So we're very interested in Africa, in the Indian example, because we'd like to know how can we transfer some of that expertise to Africa? How can we achieve the same kind of step change in productivity that's been done here? We're currently working at the Water for Food Institute in East Africa, in Kenya, and this is photographs are taken at a town called Naivasha, where we're working to bring about a step change in agricultural productivity and high value agriculture. Many of you might have heard of the cut flower industry in Kenya. There's also a very strong horticultural element to this, growing vegetables in greenhouses, and essentially making a much stronger business case for intensive irrigation-driven agriculture to improve not only the amount of crop per area of land, but also the value. And India and Indian expertise is currently very tightly woven into this. We've got Indian specialists who are leading some of the innovations in this part of Kenya, not only in irrigation and crop dynamics, but also in things like financing and logistics. There's a large, as many of you know, a large Indian diaspora living in East Africa, and it's a key part of what we hope is a transformation that is starting in this part of East Africa. And just to be perhaps a little provocative here, one of my favorite energy futurists is a gentleman called Michael Barnard. He's Canadian, and he's been looking at some of the developments happening in Africa in the last few years. So he says there in the first point that in Africa we have installed about 2.5 gigawatts of solar, and he says that that's roughly half of all the solar in Canada. He's a Canadian futurist, and he projects that next year 20 gigawatts will be installed in Africa, and the next year after that even more. And he talks also about how Africa has leapfrogged the old landline system of communications by installing cellular communications, and we're doing, or his hypothesis is that Africa is doing the same in transportation and energy. And he's talking about industrial scale power systems, power, of course, absolutely vital to irrigation, rural electricity, reliable, cheap rural power, absolutely vital to irrigation. And the key point to me that he makes is that it'll be both messy and it'll be fast. We can't predict exactly how it's going to happen, but it is happening, and it's probably going to happen more quickly than we think. And just to give you a snapshot of what I'm sure many of you know has been happening, very similar things happening in India. So we've had this revolution in electric rail transport in India in the last 15 years, which is now nearly 100% of goods are moved by rail, electric rail. And the only reason Michael Barnard says that the momentum has slowed in India is that the task is nearly finished. Solar capacity here grown from 2.8 gigawatts in 2014 to 140 installed gigawatts now, and India is aiming for 280 gigawatts by 2030. So we have completely new power systems coming into play here, driven by the falling price of solar panels, driven by government policy, driven by business sense, marketing sense. And this is something, again, we're very interested in Africa. How can we achieve some of these timeframes there too? Because as we've seen with the population growth and with the demand for food rising, we need to achieve a similar step change on the continent of Africa as well. And finally, I'd like you to think about Africa as being a strategic opportunity. It's often thought of as a problem or a responsibility, a charity case, a basket case. And I'd like to suggest that these are stereotypes from a colonial era which we should ignore, because those who still see Africa in that way are going to miss the revolution that I believe is coming in terms of energy change, in terms of output in agricultural production. So all of this leaves us with a whole range of issues that need to be considered and reconciled. We've got environmental issues, we've got climate change, we've got natural resource constraints. I mentioned briefly the global water crisis, global water shortage. We've got issues of society and culture that have to be drawn into this equation. How do people traditionally farm? How do they perceive change? How is change going to impact that? We've got the legal and institutional frameworks. Those of you who know the classic paper, Tragedy of the Commons, will know all about that. We've got some of the existing infrastructure, the need for new infrastructure. We've got issues related to that, finance, capital, land tenure, security. We've got government policies. We've got Pan-African policies. All of this amounts, I suggest to you, to a systems problem, which we sometimes talk about as meaning we call them wicked problems sometimes, or complex problems, but essentially these are problems with a tremendous number of moving parts, all of which interact with each other to produce outcomes that are very difficult for us to predict. And optimizing one part of a complex problem can lead to other parts doing things that are completely unexpected. And I'd like to suggest to you that the issue of food security and change in Africa is just exactly this. It's a complex problem with all of these facets to it. So let's just finish off now by some of the thoughts that I've had in the last few months on the growth in artificial intelligence. I'd like to suggest to you that uncertainty and vulnerability are two sides of the same coin, that if we can reduce uncertainty, in other words, then we reduce vulnerability. It's a common knowledge that ignorance is bliss, or it may be bliss, but knowledge is power. Knowledge is also, I suggest, cheaper, faster, and more lucrative than ignorance. AI can consider many of these things at once, and I suggest that AI is perhaps ideal for solving or for optimizing these complex problems. It can think of all of these things at once, we hope, and it can optimize systems in ways that perhaps our human intelligence struggles a little bit to do. We as humans are subject to prejudices, to bias. I like to think of these things sometimes as dogma. They're things we can't avoid, the ways our brains work. And I suggest that they probably hold us back more than many of us think or realize, so that a system that isn't subject to the same kinds of blind spots or the same kinds of drawbacks might be very useful in optimizing these systems problems. As all of you know, and I don't need to remind you, AI is developing extremely rapidly. This is from an essay by a futurist called Matt Schumer that came out on the 6th of February, so that's just over a month ago. And he writes provocatively in this essay that in 2022, AI battled to do basic arithmetic. In 2023, AI could pass the bar exam for law in the United States. In 2024, AI could write working software and explain graduate-level science. By late 2025, some of the best software engineers in the world were handing over part or all of their work to AI and acting only as the final check on what the AI was producing. And then he says that on February the 6th, some new models arrived that made everything before them feel like a different era. And one of the things that Matt Schumer thought was most significant was that these new AI models had partly developed themselves. In other words, the AI was thinking in such a way that it was able to realize where its blind spots were and develop itself in the current generation of AI models that are available. And a critical thing to realize here is how the rate of change appears to be increasing. And this, I suggest, has some tremendous possibilities for optimizing the complex problem of food security and agriculture that we see not only in Africa but globally. So, just in conclusion, I'd like to suggest that time is short. I hope I've managed to convey that the situation with food security in Africa is something that needs to be resolved rapidly. We can't rely on that slow increase in irrigation coverage that we've been seeing in the last few decades. We need a step change. Cooperation and collaboration are vital, and I showed you already what is happening in Kenya when we collaborate and cooperate. Hopefully that is going to grow. Small commercial farms are vital to national growth and development. So a big piece of this jigsaw is that economic growth often starts with commercialization of small-scale agriculture. And it's not just something that is to do with food security. In other words, it's something that is to do with national economic growth. So, and as I say, some of the problems that we have, some of the problems we have currently are constrained by lack of knowledge and lack of data. But I suggest that it's possible that these might be solvable as we go forward, in the same way that I'd argue we've now solved the problem of communication. I can call my brother in South Africa on WhatsApp and speak to him for as long as I want now, essentially for free, whereas even 20 or 30 years ago, that was very expensive, and 100 years ago, it was completely unthinkable. So we've solved communication. Could we be on the cusp of solving the lack of knowledge and the lack of data? I'd like to suggest that we're getting much closer to that. So I'd like to end by saying that we, I hope, are entering into an era where collaboration and cooperation between countries and between regions is seen as the way forward. This is something that is in the current national security strategy in the United States. And I hope that many of you who are studying now, some of the fantastic posters that I've seen, the work that you're doing, I hope that many of you in the next 10 or 20 years will be looking at some of these problems. Perhaps I'll even see you in Africa working there on ways to rapidly ramp up the kind of productivity that we need, using some of the tools that are becoming available through the artificial intelligence revolution. And I'd like to say then, just in conclusion, let's use it, let's be judicious, but let's use it. Time is short. Thank you. Happy to take any questions.
Yeah, so you have any quick polling question, one question?
Good afternoon, everyone. My question, sir, is that is the mining of minerals in Africa diverting infrastructure, resources, and the foreign intervention from agriculture?
That's a good question. I mean, a lot of infrastructure in Africa in the last few decades has been built as part of a sort of extractive business model where for example, a mine or a road has been built, and then the road or railway is purely to extract the commodity in its raw form, and value is added elsewhere. I think that's changing. I think that new ways of looking at the potential in Africa, not just seeing it as a source of mineral wealth or raw materials, but as somewhere where we have the youngest continent, we have a continent which is going to be one of the biggest markets going forward. So don't forget, as people get wealthier, they start to need things. They start to need everything from pairs of shoes to refrigerators and automobiles and a million and one other things. So I think there's an argument to be made that has happened in the past, but to me, it's a paradigm that is slowly shifting, and we're hopefully going to see some of the interesting impacts of that in the next decade.
Thank you so much, sir. Okay, so I think Reina.
Thank you very much.
Give it as soon as you. No issue, sir.
So, good afternoon. So I'm the person between lunch and ending the session here. So I just wanted to wait a little bit so that Dr. Cobbing can finish his talk, and there will be some repetition, but I'm going to avoid those. Basically, in his wonderful talk, he talked about the challenges, and there is, as he said, that Africa is really needing the leadership from India. So as 10 or 20 years back, you see a typical Indian family with 1 or 2 or 3 kids and a husband and wife in that motorcycle. You see the same thing now in the roads of Kenya, Nigeria, or other places. So this is what is expected right now, how these challenges, what we have solved out of necessity, can be exported to Africa or can they be imported by the Africans from here? And as Jude mentioned about the Naivasa problem, that how the Indians are in works there to solve this problem. So the population part, this is again, India is going to peak its population in the mid 70s or so. China has already peaked out. But if you look at the bottom, the countries like Nigeria or other parts of Africa, they are still going to grow beyond 2100. So this, as mentioned by in the previous talk, look at where, this is a kind of interesting slide, that the working age population growth. India, almost more or less, we are, from the baseline, the contribution of India to the increase in the workforce, I think it's peaking right now or so, but then it's going to gradually decline. And by 2050 or so, we are not going to contribute anymore to the growth in the workforce. What we have is that it's going to stabilize the workforce. So the death is going to be balanced by the new incoming workers into the workforce. But where it's going to come really, the rest, the sub-Saharan Africa or Middle East, North Africa, that area. And then the changing diets. This is one of the things that India still is a little bit insulated, but the demand for food production and the feed production. Feed is basically what we are giving to the animals. So you look at the composition of the feed, it's becoming more and more with corn and soybeans. So that is also putting a lot of pressure to produce the same thing what the humans consume. So the necessity is always a mother of invention. So the Dust Bowl, I think this is a decade-long drought in the central part of the US that basically decimated the farms. And these areas were settled in the 1860s. So not long after, like 1 or 2 generations, these people went into poverty. But fortunately, during the war, the invention of many things, especially the deep well turbine pumps, brought water and irrigation started. And I'm going to pass through a little bit quickly here. So, and this is how the irrigation started in the Central Plains. Look at the last 2 slides, the gated furrows for irrigation. Land leveling, other things happened. And then the technology went on. In the 60s, the center pivots came, and the 4 most, the largest companies, they make this irrigation system. They're located in Nebraska. They have a 90% or so market share. And as Jude mentioned that, I think these mine numbers are a little bit older, looks like. India is, as he's saying, is close to 80 million hectares. China, slightly less, maybe 10% less. And Nebraska is still a big irrigator in US. But one thing I want to mention here, that the concept of water productivity, this is basically the amount of water taken for a unit of production. So the darker the color is, more productive. So how many kilograms of corn or soybean we are getting per unit volume of water? So the irrigated areas, the right side corn, so we are getting anywhere from 2 to 2.2 kilograms per cubic meter of water. But in the dry land, you are not getting as much the case. So this is what the thing is, what Jude was mentioning, that the Africa being primarily dry land, you have low water productivity, low yield, so the demand for food is pretty high. But what it comes with, unless we reduce the water use or increase the water productivity, the demand on the water is going to be more and more. So here, over the years, Nebraska has about 100,000 wells, but as the demand went on, the well drilling also went on and on. But what is the impact of all that? The more water you take, that water you irrigate is going to go to the atmosphere. You're depleting the groundwater, depleting the streams. So if you look at the high plains of Ogallala Aquifer, that's the first slide we saw in the Jude. So the depletions have been more extreme as you go to south because the evapotranspiration demand is high. And we also see the similar story in India, Punjab and parts of Haryana. So here look at the Texas situation, the cross section, there is a line at the West Texas area. As the years are going dry, the depth of the saturated thickness is becoming less and less. In some areas, like parts of that right side that are between 100 to 125 mile range, that cross section, the aquifer has essentially gone dry. You cannot put a well and pump anymore. So these are typical problems, but again, it can be managed well. In the case of Nebraska, it's a little different hydrogeology and all that. We have seen rises in the water levels in some parts of that blue areas, but also see the decrease based on location. So then also the irrigation brings in a lot of problems. Here are the nitrate issues. High concentrations of nitrate in Nebraska. About 2.5 million hectares of land, acres of land, about 1 million hectares, under which the groundwater is not drinkable. They exceed the nitrate. So all these are all intertangled, quality, quantity. Mentioned here the water productive. I'm going to skip this one in the interest of time. So what is really helping a little bit our situation here, the institutional control on the water management, that how much you can really pump, what actions you have to take in controlling your nitrate application or contamination. So they have to have some sort of state, local or regional laws and regulations. So we have a set of governing bodies called natural resource districts. They pretty much manage the water in the watersheds. There are 23 of them. They have local taxing authority with almost $300 million in revenues. And they also allocate how much water you can pump per year or per 5-year basis here. So the area there far north, they are 33 centimeters or 36 centimeters. If you pump more, they will probably stop you. They give you an allocation, 5 years, this much is allocated. And if in 4 years you finish this, the 5th year you have to go dry. So this is not possible in many cases. But in order to comply with those regulations, then you have to go with high efficiency irrigation. So whether it's a drip or sprinkler, in our case, drip is not feasible because of the size of the land and type of crops, but in sprinkler it's feasible. And then there are various sets of things you can do to reduce your consumption. Your subsurface drip is one of them, but it's primarily for a small or specialty crops. There are many things we go through, deficit irrigation, or you can either go for rain-fed. How much time I have? I think it's a bit, maybe close up a little bit quickly. Yeah. Let me just cut down a few things here. We have been dealing with a lot of top-down approach in this country or many other parts of the world like Africa, but the things have to be more bottom-up than top-down. So if there is a problem, then how do you really solve it? Like in this one example, it's going on about 2 years. We approached the governor that this terrible contamination of nitrate or drinking water quality we have, it has to be addressed. So he was in the beginning saying that it's a legacy problem and we have done things much nicely now. But that's not the case, and when you try to convince him that both quantity and quality go side by side, he set up a task force of about 25 people, look at the problem and give me what can be done. So this March is the last meeting. So this is how things can be done. And one other thing before, since it's an AI conference, I just wanted to address one thing what Dr. Mohanty mentioned about the process-based models and how we deal with that. The crop models are getting a prominence because you can do the projections or estimation of yields based on certain traits or features. But there are, dime in a dozen type models are there. You can build a model with equations known, but where you get such data. So to do a model that is phenology based and it has really the traits or growth functions, you need to do experiments over decades. So these are outdoor chambers and they have soils in that, and they do many of these things to simulate the conditions typical for fields. But then you look at like how the leaves developed, how in the corn case, how the V2, V6 or V12 tassel, all those things are done. So you have, you basically take into three things together, the genomics, environment, and the management. But the important thing here is that you have to develop functional relationships like cotton, how the temperature is affecting your emergence to squares. Squares is the branching, squares to flowers, flowers to bolls, and boll opening and ripening, all those things. Same thing has to be done for a corn. Look at the primordia development, the temperature, leaves, and then all these things all group together. Once you have these functions developed, then you look into your stress factors, like whether it's a moisture stress, thermal stress, or you have nitrogen stress or carbon stress. With that, you have to form the models. So this is how the models are basically developed: experiments, mathematical functions, integrated into functions, and then you have to have some user interface and run these models. So I'm not going to go that much into it because we are doing this training course on the models on March 17, and many of you from this university and here in India and other places are taking place, participating. But since these models are developed with the phenology, with all these things, if your germination date is right, which is becoming more and more, as Dr. Mohanty was saying, that germination is one of the key factors. But you look at the machinery, if you have a $1 million tractor, and the John Deere machine is going to push the seeds back nearly close to the same bulk density. So the moisture is going to be pretty much similar to what would have been in the undisturbed soil. So if your field can have near uniform emergence, then V2 or V6 or V8 with proper nutrition, and if you have much control over the environment and all that data, you can estimate. If there is something shifting, then you can make those adjustments. So by week, you can do the yield estimate or change your estimation based on what parameters are driving those. So one here, the AI-driven thing we have done, but it's basically coming out of the more complex crop models. But these are soil process model, the atmospheric, the stromatal conductance-driven evapotranspiration model, and the crop growth model together. Basically, the idea was that can we estimate the cotton fiber length or fiber strength using models. Why is important? Because the bale price, the cotton bale in the US can be between $800 to $1,100 depending upon the length or strength, how they are. If these models can really estimate that based on your environmental factors, genomic factors or others, management factors, then the farmers are going to be pretty much happy to see that, okay, I know my bale is going to be $200 to $300 more. And so this year I'm going to be in better shape. So this is where USDA basically was interested to see that if we can give the farmers based on the planting date, what might be the quality, the cotton fiber quality or strength or length of these fibers produced by the bolls. So this is one where the AI was helpful. It's basically the cotton model is called the GOSIM. So 5 years of data. They're good. We're going to skip it now. Then one more thing we did is corn yield forecasting in the Midwest. Also same thing. But these process-based models, when they become so heavy to use, as Alagmanda was mentioning, then this is where the AI can be introduced, and based on the thousands of simulations, maybe on your phone you can get based on the three parameters what you are inputting, the genomic parameters, the hybrid number or hybrid type, your environment, what you are putting from the rainfall, irrigation and all that, and the management and the soil factors coming from the environment, sorry, and the management, irrigation and all those. You can do pretty much similar calculations based on the parameters you are looking at. Yield as a function of temperature, yield as a function of moisture, all those things. So one last example here is that sometimes we can do a number of the TAPS is a project we have. This is testing agricultural performance solutions where you can try various scenarios at a risk-free environment. Like if you do at your own field, you can take a hit in your yield, something goes wrong. But here we give you the willing farmers maybe few hundred fields to try, and you can decide your own irrigation, own temperature, own marketing, own seeding rate, on nutrition, all those things, and then estimate there are some prices and all those things. But we took that set of data and tried to run the model. Basically, it came out very clean that you do not need that many parameters like typical crop models need, because these are phenological based and very tied to the growth functions, and they are adjusted weekly based on the irrigation and other factors. So they're pretty successful. And I think with that, I'm going to close because I'm running a little bit time-wise. But
thank you so much. Thank you.
Any questions, or we can?
Any questions for Dr. Ray?
Maybe if you have, keep it one line only. Yeah, I think that's a good. Maybe people did not hear you, Dr. Ponda. I'm going to repeat for you that there is a panel in the afternoon. Please hold some of your questions. Yeah. That might be a better venue to. Yeah.
All right. With that, then we close this session. Thank you so much for attending.
Sir, let's have a big round of applause for our chairman, sir, who has nicely chaired. Sir, we are thankful to you, indebted to you, sir, for your nice conduct of this program and for your elaborate talk, sir. We are indebted to you, sir. We are equally indebted to our speakers, like Madam Dr. Alkananda Maitra and Professor C.R. Rai, Dr. Jude Cobbing. We are all thankful to you, sir, and we look forward for such discussion in the panel in the afternoon. I request the faculty members, please do come and take part so that students, faculty members, researchers can have a better interaction. I also thank both the rapporteurs for being patient enough to record the proceedings. With this, we end up the first session, and we can say this was completely an overseas session, and I must thank the organizing secretary for organizing such a nice session. With this, big thanks to all. Let's break for lunch. 2:30 sharp. Friends, 2:30 sharp, please join for the poster. Please join for the poster. I repeat, 2:30 sharp. And, okay, 2:45. Okay, extended 15 minutes to 45. But let's be 2:45 there, and by 3:15 or max by 3:30, we should start the panel. And here in this hall, I request everybody to be present because I believe that will be more live and we can take more questions and we can have a threadbare discussion. Thank you very much. Thanks all. Let's break for lunch. Lunch is arranged just in the left side of this hall, outside just hall. And you can go to the food court and have the lunch, sir. Thank you so much. Thank you, all of you.